My name's Cyrus. I work at Lawrence Livermore. I work on VisIt, Conduit, and Ascent. I'm going to talk to you a little bit about all those things throughout today, but a big focus of this is VisIt, the visualization tool that we work on. And first I want to get started by thanking our sponsors. So there's a lot of folks that have poured money and time into VisIt. But I want to thank here Lawrence Livermore, the ASC program, and also the ECP project. So here's the plan. So I'm going to do some slides. We'll aim for 15 minutes, and we could also have maybe 5 minutes more if we need to. And then after lunch, we're going to come back and we're going to do hands-on. So I'm going to have this in 2 parts. So one's going to be kind of a whirlwind tour where I go through things pretty quickly just to give you an idea of a lot of capabilities. And then the other half of it's going to be a slowed down hands-on of a blood flow simulation, and we'll go a little bit slower. But I want to point out that all of this information is available on our wiki pages and things through the link. So if there's some detail that you didn't hear me say, you can get back to it. Right. So for the tutorial, we'll be using our latest release, which is VisIt 3.3. Here's a couple links here. Our project is fully hosted on GitHub now, so that's where you can contact us. That's where the code is. That's where you can file issues and do discussions and things of that nature. So there's some links to get you there. You'll see them several times just so we can kind of burn them into your brain. And then another thing here to acknowledge is some of our data sets that we've used. So we've used this aneurysm simulation data set for many years. It's been nice to have this kind of condensed data set that's a little bit more interesting than some of our toy data sets. So thanks to the Swiss Supercomputing Center folks for giving us that. And although we're not going to touch it today, you could follow along with this. There's a potential flow simulation data set that was created using InFM that you could also download and do similar exercises with. All right, so let's get moving. So VisIt project introduction. So VisIt's an amalgam of the word visualization and it. We used to joke about how it's hard to Google it. However, Google knows a lot about you. It probably knows that you're a computational physicist or scientist or whatever, and it might actually know you want this. If it doesn't, you can always just Google LLML VisIt, and you'll end up there. And of course, for me, it knows I've been here many, many, many times, so it always pulls up for me. So what is it? So VisIt is an open source tool for looking at simulation data, mesh-based simulation data. So that means that, the context we have here is embedded in space, and there's details about all that. It's an end user tool, right? So it's made for visualization experts like myself, but it's also made for folks who do simulation, right? And are running the simulation codes and need to get in and deal with their data. Works on your desktop, works on the largest supercomputers, and it's open source, so BSD style license. So this picture here is actually from quite a while ago. This is from 2006, I believe. So it's the rainbow lasagna or the moldy lasagna, depending on how you think of it. So it was a pretty large data set at the time. Actually, it's still a pretty decent data set for today. It's a Raleigh-Taylor instability mixing problem that was run on the original BlueGL computer at Livermore. So what do people use VisIt for? Joe covered a couple of these things in the morning. The primary way that people use VisIt is for poking around at their data, right? Although all of your simulations have ambitions to be on the cover of Nature or win Gordon Bell Prizes, they don't always make it there, right? Usually you're sitting there and you're kind of interrogating them. You might be cutting them in half and things. So that's what a lot of people use VisIt for. They run and they go in and they get in there and they ask questions about their data, as part of their daily or weekly workflow. So there's also features there for quantitative analysis, so things like integrals, right? Getting curves out, line outs. Joe has the greatest example of visual debugging, right? He showed you this morning where the propeller just vanishes, right? Those types of things are very hard to understand without a visualization tool. So people do use visualization tools for debugging, and that includes like picking and really thinking hard about your masses and all kinds of stuff, right? Another important use case is comparative analysis. So if you have multiple runs or even multiple slices, time steps of the same data set, oftentimes you want to compare them. Of course, you can use your brain's neural networks to do that by making multiple images, right? But you can also map meshes onto each other and do subtractions and things like that, and VisIt supports that. And then finally, presentation graphics, very important, right? You do need to make pretty pictures. They're very powerful for communicating things, so we have things for that, for making movies, et cetera. And we have a whole suite of tools for different visualization primitives. Joe talked in details about a lot of these, right? Streamlines, pathlines, using glyphs for looking at vector fields. The bread and butter visualization is really pseudo color plot. That's what most people use most of the time. Volume rendering, so that's a ray tracing method where you send rays through your data, kind of like an X-ray. And there's a couple other things. So we have some molecular visualization support. And we also have a parallel coordinates plot, which is primarily used to think about data in the context of another plot. But it's one of the few InfoVis things that we have. So VisIt was started at Livermore around 2000, supporting our large-scale physics codes. So VisIt was forged in the hallways where there were VisIt developers and computational scientists who would come to their door and say, I absolutely need this to work. So that's really where it started. But over time, it grew. It grew with other funding streams, including the Office of Science, and it became a fully open source project. Around 2008, we moved to do development out in the open. And we have lots of collaborations with folks. Our most recent evolution of all of our infrastructure was moving everything to GitHub, which was kind of a big deal. And we did that around 2019. So we're also involved with the ECP project and things of that nature, right? So we have connections to all these different communities and help support them. So VisIt uses VTK under the hood. There's a couple other things that are built around or on top of it. But primarily, you can think about VTK as being the construct that we use to pass around mesh data. So it supports, points, curves, 2D, 3D, rectilinear meshes, up to unstructured meshes. Primarily, everything is linear. There's some quadratic support. There's also some support for MFIM that does refinement if you're a high order person. And in addition to these different types of meshes, we support all kinds of different fields. Normally, you think about scalars or vectors, like pressure or density or scalars, and vectors might be a velocity, right, a vector field. But we also have stuff for material volume fractions. So, if you have multi-material simulations, and also species, which are like atomistically weighted or mass-weighted things. So we have binaries for all kinds of different platforms, lots of versions of Linux these days, because we can use containers to build those, also Windows and Mac. So you can download those. So it's also installed on a lot of different centers. So I'll show you how to connect to Cooley's installation later today. If all else fails, if you have a very exotic laptop or something like that nature, which I've seen at ATPESC before, you can be brave and build VisIt yourself. So we do have a script to do it, and that's the script we use to build all our releases. It's not for the faint of heart, but it is possible. We also have some support for building with SPAC, so if you're interested in trying to try that. But start with a pre-built binary at first. How do you get your data into VisIt? So we support more than 110 different file formats. It's probably, I don't know, that number goes up, right? This is everything from well-known, well-published standard formats to some guy down the hall really needed something to get his work done, right? So there's a range of support for these different things and a range of capabilities in them. The recommendation that we have, if you're just starting, is to use a commonly used format that lots of other people use. So examples are Silo, VTK, XDMF, some of the parallel VTK formats, and then also Blueprint, which is a thing that we've been investing in a while, which allows you to write meshes in either JSON, YAML, or even HDF5 files. There's also a manual that can help you make decisions about this, and there's a writer utility that helps you, like for simple cases, you could look and compile and do things. Use a file format that other people are using is always a good place to start. So VisIt itself is extensible. This comes in a few different flavors. I think our database plugins, the way we have those 110 different supports is we have a plugin infrastructure that allows people to write something that can just get their data digested into VisIt. We have Python interfaces, which are used heavily. The primary one is the scripting interface, or we call it the command line interface, and I'll show you about that today. And then we also do have support for in-situ coupling of VisIt itself. That's called libsim. All right. So VisIt over the years, one of the exciting things about it is it's also been used as a platform to deploy visualization research and actually to do visualization research. So particularly at the largest scales with this distributed data, It can be hard to have an infrastructure to write your algorithms, so people would use VisIt's infrastructure in order to try to figure out how to prototype algorithms and then also have a vehicle to get it into people's hands. Currently, we've been spending a lot of time on in-situ processing and also addressing node-level parallelism. That's all these heterogeneous architectures now. So we have AMD and NVIDIA and Intel GPUs, all that stuff. So that's where a lot of effort's been focused over the last few years. I mentioned this already, but VisIt 3.0 was a big change in process for us. So we migrated all of our stuff to GitHub, and we migrated our old manuals, our old issue trackers, our old source, all that stuff. So everything's on GitHub now. It's under the VisIt-DAV organization. And we're using GitHub discussions to support, discussions. So user support, which has been helpful. So it's nice to be able to share answers with other folks easily. Just looking at recent history. So the 3.2 series, which was over the last, the last year or so, that was when we finally got Python 3 support fully worked out. So that was a big deal. VisIt can still build with Python 2 if you have to be there, but a lot of our distributions are Python 3 now. And then our most recent release was a month and a half ago, VisIt 3.3. A lot of good stuff in there, investments in the blueprint stuff, like I talked about, improvements to some of our capabilities for doing simulated diagnostics, lots of plugin updates. And if you'll notice now, there's 100 bazillion color tables, which actually we're working on making a better UI for, but there's a lot of them in there now. So those are a couple of the new things, most recent things. All right, so VisIt uses MPI for distributed memory parallelism. So what does this mean, right? In your mind, you have this picture on the left here, which is your giant data set. But the way that this has to be processed on the supercomputer is, it has to be carved up for the individual nodes to do their processing, right? So in this example, this is the same lasagna, but a little bit different look at it from before. It was so this is what you see, but it was actually partitioned in this way, right? So the individual MPI tasks would have some subset of those chunks, and then the algorithms are adapted to work through that. We have this client-server infrastructure. What that means is that the viewer you use, the thing you interact with, is really a client that's talking to some engine that does the heavy lifting. That can either be on your computer or it can be on a HPC cluster. And then other things like there's a GUI and there's a command line interface also talk to that viewer to set everything up. To you, you think about things in this world in terms of how you interact with it, and then that's an implementation detail of where the heavy lifting is happening. To do things distributed memory parallel, you have to have special algorithms to do this, right? So rendering is one that you have to, right? Because you have to do things right. You can render the individual pictures of all those things, but then you have to occlude things based on depth and et cetera. So we have parallel compositing to do that, to make sure you get the right picture. We also have our volume rendering does this in parallel as well. All right, so this is important. This is where we've been spending a lot of effort over the last several years. So the visualization community as a whole knows that we have some changing, the world's changing for exascale, which we're on the bridge of, right? And there's really two aspects of that we've been working on addressing through various projects and collaborating on, right? So you've heard about VTKM. So VTKM is a solution for the on-node parallelism changes, right? So we need to leverage, very thin threads on GPUs, right? That's a way to think about it. So it's the tool that's giving us the ability to work on Intel machines or NVIDIA machines or AMD machines and effectively use those resources on node. Another big scariness is what Silvio talked about this morning about the I/O gap. We have really, really fast supercomputers, and they're getting faster and faster in terms of their compute. However, their I/O stuff isn't keeping up, right? Just based on the way things are going. So we want to be able to do things more in situ, or in memory. So we want to have capabilities that allow you to leverage this thing while the data's there, and it doesn't have to go all the way back out through a file system and all the way back in. So the Alpine project in ECP is one of these efforts, and there's different infrastructures that help solve this as well. So ParaView's Catalyst, VisIt's LibSim, Sensei, which you heard about, and Ascent, which I'll teach you about a little bit later. So I'm personally involved in two things, and the VisIt team as well involved in creating these two things. So Conduit is a tool that we created several years ago to help us make it easy to share in-memory data, just generically in-memory data, and then also things like meshes. So that's been a big investment for us to get to this in situ infrastructure that we want. And then also Ascent, which is a flyweight in situ visualization. So it's a smaller thing. It's not going to have the long tail features of something like VisIt or ParaView, but it's meant to do the basic stuff in situ easily and be easier to build. So in the interest of time, I can talk about you're going to learn about Conduit and Ascent later, so I'll skip through these things and we can talk about them a little bit more in the afternoon. But you can link to their project sites here and you can figure them out. All right. So let's see, how am I doing on time? Can someone tell me? 12:30, okay. We can do this, 5 minutes, you guys okay? All right. All right. So when you learn about using VisIt, I'm going to teach you kind of the 5 core things you need to think about when you interact with the tool. And then when we come back from lunch and you're all fed and happy, we'll actually put these into place. So VisIt has 5 building blocks that you should think about. So databases are how you get data into VisIt. Plots are how you make pictures or render things. Operators are how you transform data in a particular way, like a slice or a threshold or something like that. Expressions allow you to create derived quantities. So I'll talk about what that means in a little bit later, but it allows you to do some processing from existing fields and create new fields. And then queries allow you to summarize data, like do integrals, et cetera, right? So 5 things. I should only hold up one hand if I say 5 things. And when you're thinking about using VisIt, you can think about using these combination of 5 things in order to get your work done. Couple examples we'll show. Simplest thing you can do is you have some data, you want to make a picture of it. So you use a database to open up a file format. It could be an HDF5 file or a VTK file, et cetera. And then we're going to add a plot, and a plot will allow us to render it and create some visual representation. So in this example, we say, hey, let's open up some HDF5 file that has a field in it, and I want to make a pseudo color plot of the density of that. So we'll have a picture like you saw of the rainbow lasagna before, right? That's the workflow here. Now, expanding upon this a little bit more, we can add in an operator. So if you have an operator, you can do things like slice, right? So you had a 3D data set, but you only care about a plane, right? So we start with our database, we apply our operator, which takes a slice, and then we add a pseudo color plot. Well, now we're not looking at a pseudo color plot of a volume, we're looking at a pseudo color plot of the slice that we pulled out of there, right? Makes sense. So we build these pipelines and we combine these capabilities to get what we're after. You can use a lot of different operators. So say you had a slice, but now you want to turn that slice into a mountain, right? Based on the field value that's there. You can do that with an elevate operator, right? So you can combine these things together, and then at the end of the day, you're plotting whatever is the result of that pipeline. Another thing you can do is, say you've published some sort of data, say you have a vector field, right? But you're interested in a different representation of it, or you're interested in combining that field with something else to calculate something on the fly. That's what expressions are for in VisIt. So in this example, you have a vector field called velocity, but you'd really like to look at it as a scalar. So you can take the magnitude of that vector field, and then you can get a picture of that you can plot with a pseudo color plot, right? So that's what expressions do. Queries, last thing, allow us to do data summarization. So we can extract quantitative information, so like integrate all the density to find mass, or find the maximum point in my data set, right? Stuff like that. So that's what queries allow us to do. You could think of them as happening at the end of the pipeline, like after the plot happened. And you can go bananas with it. You can combine all these things together in different ways, right? So if I look at all the things that I just told you, it's possible to use those all together to answer a series of questions. We're looking at the speed, which is an expression of this vector field, the magnitude of it, and then we want to do a query over a cross-section, which is a slice, and et cetera, et cetera. So I'll show you examples of how we put these things together, but this particular example isn't important. The thing to think about are the 5, kind of the 5 basic building blocks that we have here. So databases, databases, plots, operators, expressions, and queries.